Welcome to Starstream, a new blockchain VM. It's a reimagining of UTXO smart contracts based on first-party coroutines. Now, this is a non-technical overview. We have a different video that's a more technical overview of your developer. For this video, we're going to go over a few key points. The novel design of Starstream, the use scalability it unlocks, the use cases it helps build, as well as the roadmap for integration into chain. So, what is the core concept of Starstream? Is that the most successful systems are built by taking a core idea and trying to take it as far as you can. So, for example, Lego started off with just very simple bricks, yet it's enabled people to build wonderful, complex creations. And so, in the same way, we want a simple concept when designing a VM to have as little amount of code as possible in the actual virtual machine implementation. The reason why is because we want it to be easy to understand, which helps developer onboarding to get more developers into the ecosystem. We wanted it to be easy to develop with this VM. This lowers development costs and also makes it faster to develop your cool dApp as well. And obviously, super importantly, we want it to be super easy to audit, which leads to much safer dApps. So the key insight is that simplicity often outcompetes complexity when it comes to critical systems. So in Starstream, we decided to take as our abstraction that everything is a coroutine. But what is a coroutine? Especially if you're not technical, you might not have heard of this term before. So imagine you're writing a computer program to calculate pi. Now, pi, as you might remember from high school, is an infinite number. It never ends. And so the calculation for the digits of pi is also infinite. So if you want to write a computer program that runs pi, you don't want to just leave it running forever, taking up all your CPU. You like to leave it in the background while you browse YouTube, browse Reddit, browse Twitter, or whatever other sites you prefer. And so you want to compute in the background, but not block your entire computer from doing other tasks. So how do we achieve that in practice? How do we avoid this kind of blocking? Well, more generally speaking, computers nowadays can run multiple different applications in parallel, right? You might be reading a PDF file, you might be using Discord, you might be using Telegram. So how do we make your computer feel responsive despite running many different applications? So in the past, computers ran one program at a time, and this made computers feel unresponsive because you couldn't have background tasks. Nowadays, computers try and have every application take turns in very small chunks. So it runs one application for a very small amount of time, then runs the next application for a very small amount of time. And so each program makes a small amount of progress. This makes your computer feel more responsive because it can feel like you actually have multiple programs running at the same time, even though in practice, they're running sequentially. Now, if you're technical, you might know about different cores on a CPU, but I'm kind of abstracting away from this for the non-technical people in the crowd. So when we're thinking about giving every program a small chunk of time to run, this is kind of similar to blockchains, right? So in a regular computer, you'd have different applications running. In the blockchain context, you have different dApps running. So in a regular computer, your operating system would be in charge of which program gets scheduled to run at which point. But in the blockchain context, it's the block producers that are running the network that get to choose which transactions to process at which time. And so what are coroutines? Now we have this background. So coroutines are a model to allow execution to be suspended and resumed. So it's a kind of programming paradigm, it's a way to think about code that's gained a lot of popularity over the past few years. So some languages have been early adopters that have implemented coroutines a while back, but a lot of other languages are implementing these now. The latest being Wasm, that's only having this as an experimental feature fairly recently, as of last year. And so, what do we care about these coroutines? It's great that they're useful for thinking about blockchains, but how do we actually write programs using these? Well, you can think of the program history as now a series of partial computation. And so the key insight is that we can use the UTXO model to represent this history of a programming evolving over time. So why do we care about coroutines in practice? How does this actually help the user experience? Well, there's existing UTXO-based smart contract programming languages you might have heard of. For example, Eigen. And in Eigen, coroutines are not a first-party primitive. That means that developers have to think about the history of their program and how to encode that their program has to pause and continue at a next step. And so you can see an example NFT Mint contract on the right-hand side where all the purple code is purely to make sure that the next step of the program is processed properly. So it's a lot of overhead, not just in lines of code, but in mental overhead. You have to think about, okay, how do I handle the fact that my program might pause, and how do I make sure that when it runs later on that it's being called in the right way in the right time. So in Starstream, we have coroutines built in as a first-party primitive. It allows the implementation of the same contract to not just be a very few lines of code that's not only simpler to read, it's also simpler to write. So of course, now we have Starstream, we have this wonderful developer experience. But developer experiences are not everything, right? We want to have more than developer experience. We want to unlock new features, new things that we couldn't do before. And so I'm happy to say that Starstream gives you this as well. So notably, you might have heard of a concept called ZK, which helps with scalability and privacy. And so there's two key features it gives you. So one is compression. It allows you to represent batches of transactions in just 16 kilobytes. So remember, in Cardano, a maximum transaction size is around 8 kilobytes. So around the size of 2 transactions. So what is transaction batching useful for? Well, it's useful for real-world assets. So for example, you have a traceability app. You want to trace the history of a wine bottle from city to city to city. You might want to batch multiple updates to the state of a wine bottle into just one single entity. So it allows you to batch. And so ZK helps you with that. And so a lot of real-world asset use cases use ZK for scalability. It's also really useful for DeFi. So DeFi, you might be familiar that it often requires a lot of transaction chaining, right? You want to lend an asset, then swap that asset on a DeFi on a DEX, and then take that asset you just swapped and then use that to interact with some other DeFi protocol. So there's a lot of composability and chains of things going on. And so ZK can help with that because it can allow you to express that entire chain as a single unit of 16 kilobytes. So you can queue up, 100 different DeFi apps, but still have it fit inside a single transaction on chain. So it helps a lot with DeFi. It also helps a lot with gaming scalability. So for gaming, users are making very, very frequent actions in a game. And so you can represent the entire gaming session of a player, which is a single 16 kilobyte block. So this is great for a lot of these high throughput use cases. ZK can also give you data protection. So not every chain gives you this, but Starstream does. It allows you to transact without revealing private metadata. So it gives you data privacy. This is great for real-world assets, for regulatory purposes. You might have information that you need to keep for regulatory purposes, but you might not want to reveal on-chain. It's also great for DeFi, where you want to avoid being front-run so you get the best deals possible. And it's great for games, because in a lot of games you want fog of war, where you can make an action without revealing the state of your board to the opponent. So ZK is this great technology that, as you can see, helps a lot with a lot of blockchain use cases. And one of the popular hot topics in ZK at the moment is this concept called incrementally verifiable computation, otherwise known as IVC. So what is IVC? So IVC is a cryptographic primitive for proving correctness of an iterated and incremental computation. And you might notice that in Starstream, we're already modeling programs as a computation over time, as an iterated and an incremental computation. So actually, Starstream is really easy to model using IVC, which makes it super easy to ZKify Starstream. And we can expand this even further, right? So the core idea of Starstream is we model programs as plausible functions, which are coroutines. So what does it mean to call another smart contract? Right, you have a DEX, and you use that. Then you call into a liquidity pool. You call into a lending protocol. Right, you're chaining transactions together. So when you're calling another smart contract, it's like pausing contract 1, going to contract 2, executing that, and then coming back with the result. Right, you swap on a DEX. You take the result of that DEX, you provide it to a lending protocol, and then you go back and then you swap on a DEX again, something like that. Right. This is also just function pausing, which we easily model with Starstream. And we can take this even further, right? So in Starstream, we're modeling the lifetimes of programs as UTXOs. What else has lifetimes? Tokens. So tokens can also just be coroutines, right? The mint is the start of the program. Transferring the token around is like iterating the program. And then the burn is the end of the lifetime of the program. So Starstream really easily handles tokens as well. So notably, you might notice that just with one single primitive, we get a really holistic solution. Right? In previous approaches, you had these layers of complexity, right? How do we handle transaction batching? Well, we have a new kind of thing we're developing for that. How do you ZKify a smart contract? Well, every smart contract will have its own ZKification method, and sometimes it might be ZK, and sometimes it might be not. And so you end up having all these layers of complexity that just make it hard to think about how the system works, for the system to learn, and importantly, it makes up the system becomes a very large thing, which is hard to update and hard to audit. In Starstream, we just have a single concept called coroutines. It handles everything. It handles the tokens, it handles the smart contracts, it handles the ZK, it handles transaction chaining. It just makes everything so much simpler for the implementation and the conceptual understanding of what is Starstream. So let's look at some use cases that can easily be handled with Starstream. So for example, oracles, which are historically hard to do with the UTXO model. The reason why is because you have some off-chain data source that's updating, for example, the price of gold. And so every time the price of gold updates, you create a new UTXO that's the new price of gold over time. So every time the price changes, you update a new UTXO. So from that perspective, how do you consume all this data? Well, before Starstream, you had this issue where you have too much data to process a single transaction, right? Maybe the price of gold has updated, 10 times, and you want your DApp update to reflect this. Well, transactions have a maximum size, and so there might be more data for you to process that you can do all atomically, which is very hard, not only because it causes this weird thing where you have to have the data be partially updated. It also means that you as a DApp developer have to handle these partial updates. Like, what if there's more data than I can handle? Okay, well, in that case, I have to do a partial update and then let people know it's a partial update, and I'll have to do updates later. So this introduces a lot of developer complexity. In Starstream, we don't have this problem because we're already modeling programs as a possible iteration of code. And so when we get to transaction 2, if we can't fit everything together, we can just split stuff into transactions, and we're already modeling stuff as possible functions. So it very simply gives you the ability to continue from where you left off without any additional developer mental overhead. And in fact, we can go even further than this because, as I mentioned, Starstream is so easy to ZKify. You can just batch everything together. So you can say, okay, I'll just update UTXOs 1 to 1,000 all in just a single transaction in one ZK proof of 16 kilobytes. So this ability to batch that together in Starstream makes implementing oracles so much easier for developers. And, this is just one of the use cases that it simplifies. Another thing is simple stable coins, or just tokens with constraints in general. So why are stable coins hard to implement in other systems? Because there's a lot of mental overhead of different types. What's the type of transaction? What's the type of a token? What's the type of a UTXO? What's the type of different smart contracts? What's the context? What are the different wrappers you might have to handle? There's so many things going around that's hard to figure out how to restrict the state of the system. Because remember, in stable coins, you want to say okay, you can only transfer the stable coin if you're not on a list of banned addresses by the government. Or for example, another example of something that's like stable coins is enforced royalties, right? We only want NFTs to be tradable on this NFT marketplace if they've paid a royalty, right? Or for example, in a game, you might have a token that can only be transferred if you've completed a quest, right? So it's very common to have tokens that can only be sent based off constraints. But if you have so many different ways to represent state, it's very hard to figure out how to properly restrict that state. In Starstream, we have just a very simple system, which is that there's just this coroutine. And so you can very easily figure out how to represent the state of a coroutine, the valid state of a program, and solve this problem easily. So notably, in Starstream, you can model coroutines with inputs, outputs, and effects. And this basically gives you the API of your program. And because in Starstream, everything is just the coroutine, but having this very easy way to specify the API of your coroutine, it automatically gives you an API for tokens, an API for UTXOs, an API for transactions, an API for ZK. So you no longer have to have all these different APIs that have different formats. You just have to find one thing, you automatically everything you're free. It makes it super easy to create these kinds of tokens with different constraints. So this makes it super easy to make tokens based off regulatory requirements like stable coins and real world assets. It also makes it super easy to build different token standards you might want for different use cases, like soulbound tokens, which are very popular for games, or enforced royalties if you're dealing with NFTs. Now, you might be thinking oh, Starstream is super good, but how far are you? How is the progress on this going? And I'm happy to say we actually already have the code for Starstream on GitHub. Of course, this is still a work in progress, but we already have proof of concepts of things like tokens and patching and browser support. You can already run Starstream in the browser. We're actively working on the ZK implementation that I've mentioned. And we even have a Discord working group with over 50 people in it from 22 different companies. So there's a lot of interest in Starstream already. In fact, you can contribute to Starstream today. So I have on screen the Discord link for our working group, and you're welcome to scan that, or I'll also have the link for you to click on below. And so you can think of Starstream as an alternative to Plutus or EVM, these other different virtual machines in the blockchain space. But I think it's developed in a way that uses latest techniques to give you a lot of really clear benefits in a way that does not introduce a lot of complexity. So super excited to have been working on Starstream as kind of like a project that we've been working in the background, and super happy to announce it today of all the progress we're making. And we think we have something really awesome. And we're building this as a public good. That's to say, this is not something where we're keeping for ourselves and we'll have be the only people working on Starstream. No, this is a public good. Anybody can contribute to Starstream. Anybody can use Starstream. So definitely, if you want to contribute, join our Discord group. And if you want to know more about technically how does Starstream work internally as a developer perspective, as I mentioned, we have a separate video on that goes more into the code and how Starstream smart contracts looks like in practice. So if you're a developer, definitely check that out. And thanks for the time.